Hi guys, welcome back to my channel. Today we'll be looking at dimension and dimensionless quantities. In our previous video, we talked about physical quantities, and we said basically they are divided into three fundamental and derived quantities, which has been successfully dealt with. Then we said we have dimension and dimensionless quantities, and lastly we have the scalar and vector quantities. Then I gave you few exceptions. There are two special quantities like that called supplementary quantities: the plane angle and the solid angle. Please, if you have not watched that video, you can go back to that and watch it. So today we are looking at dimension and dimensionless quantities. What are dimensional quantities? Dimensional quantities are those quantities that can be expressed in terms of the dimensions of two or more fundamental quantities. So before we go fully into looking at the dimensional quantities, let's first look at the dimensions of the fundamental quantities. The fundamental quantities, they have their own dimensions. So any other quantity you can now express in terms of the dimensions of the fundamental quantities are what we call dimensional quantities. Okay? So let's look at the dimension of the fundamental quantities. Units and dimension. Remember, we said we have some fundamental quantities. Okay? We said we have length, whose unit is meter. Dimension of length is capital letter L. We have mass. Unit of mass is kilogram. Dimension is capital letter M. We have time, whose unit is seconds. Dimension is capital letter T. If you look at the first three, we make use of the capital letter of their initial, right? Then we have temperature, whose unit is Kelvin. Dimension is theta. We have electric current. Electric current, whose unit is ampere. Capital letter A. Then dimension is capital letter I. Capital letter I. Then we have amount of substance. Amount of substance, whose unit is mole. Mole. Dimension is mil. We use mil for that. Then lastly, we have luminous intensity. Luminous intensity, whose unit is candela. We use CD for that. So dimension is J. The last two are not common. In fact, some people don't even use these two as dimension, just leave it blank. But the first five are very, very essential. 1, 2, 3, 4, 5, 6, 7. So the first five are very, very essential. So these are the common ones we use. The last two are not common. All right? So these are the dimension of fundamental quantities. For the dimensional quantities now, they are the quantities we can express in terms of the dimensions of the fundamental quantities. Okay? Before I go fully into that, let me quickly show you what are dimensionless quantities. Dimensionless quantities, as the name implies, they don't have dimension. As a matter of fact, they are the ratios of two or more quantities that have the same unit. So that means that they are unitless. Any quantity that is unitless will surely be dimensionless. For instance, examples of dimensionless quantities, we have strain. Strain. Strain is extension over original length. Extension over length. Unit of extension is meter. Unit of length is meter. So they cancel out. Does not have units. It's a good example of dimensionless quantity. Strain. Magnetic susceptibility. Magnetic susceptibility. Susceptibility is another example of dimensionless quantity. We have relative density. Relative density is another example. We also have relative permeability. Relative permeability. relative permittivity. We also have magnification, and so on and so forth. All these ones, they are dimensionless. Okay? Now, the process of obtaining the dimensions of various quantities is what we call dimensional analysis. So let's look at dimensional analysis. I will be obtaining the dimension of some quantities, few of them. Okay? And I will start with the simple one you know. Let's start with area. One thing about dimension of quantities is this. You can use any formula where that quantity is present. Any formula where that quantity is present can be used. Like area, we have various formulae for area. We have area of rectangle, which is length times breadth, area of square, n square, then area of circle, pi r square. I can use any of those things to get the dimension of area. But let's use the common one, length times breadth. Length L times breadth or width. Okay? So formula for area is L times breadth. Units now. Unit of length is meter, right? What of breadth is also meter. Why is it meter? Remember that area is a derived quantity, and we said derived quantities, they are obtained by multiplying or dividing two or more fundamental quantities in the previous video, right? Now, when I was giving the fundamental quantities, I didn't give you breadth. We have length there. And area as a derived quantity, it is obtained from fundamental, right? Now, breadth is there. Why is it that we are using breadth when it is not part of the fundamental quantity? It is because breadth itself is a form of length. As a matter of fact, length has various names. The following are called lengths. So anywhere they appear, they perform the function of length. We have breadth, width, height, distance, displacement, circumference, radius, diameter, amplitude, and so on and so forth. All of them, they have the same unit as length, which is meter. Okay, so breadth is also a fundamental quantity, a form of length, right? So unit will now be what? Meter squared. Then there's another thing we call base unit. Remember we said the fundamental unit can also be called base unit, right? In this place, the base unit will not change because meter is still a fundamental unit, so it won't change. Why am I introducing base unit? It is because there are some quantities that have their own specific units. For example, force. Unit of force is Newton. If all what you know about force is, as far as unit is concerned, is that its unit is Newton, by the time they ask for the dimension, you'll be able to do it. Because Newton is not a fundamental unit, but we can still break it down so that it conforms to the fundamental unit, and that is called base unit. Okay? So dimension now. Dimension of area will now be L squared. Then number 2, let's look at volume. Volume is length times breadth times height. Breadth is B, height is H. So V is L times B times H. Unit now. Unit of length is meter, breadth is meter, height is meter. So that gives us meter cube. Base unit will still remain the same because meter is a fundamental unit. Dimension now, that will be L cube. Okay, let's look at another simple one. and that is density. Density is mass over volume. Mass over volume. So rho is m over v. Unit now. What's unit of mass? Kilogram. What about volume? That was the last thing we did. Unit of volume is meter cube. And that can be written as kilogram per meter cube. So base unit will still remain the same. Kilogram is fundamental unit or base unit. Meter also. It won't change. So dimension now. Kilogram is capital letter M. Meter, that's capital letter L raised by minus 3. So this becomes the dimensions of what? Density. Let's look at speed. Speed, that's distance over time. Once you know the formula where the quantity is present, then it becomes easy. Dimension is very easy. Distance s over time. Some use x for it, some use x. Some even use d for distance. Okay? S over t. Unit of distance is meter, time is second. So that's meter per second. The base unit also remains the same, it will not change. Then dimension will be dimension of meter, that's capital letter L. Then for time, this is minus 1. Alright? Let's find another one. Let's look at velocity. Velocity V. That's displacement. Displacement S over time. Speed and velocity, they have the same units, right? But speed is a scalar quantity. Velocity is a vector quantity. That's why I put arrow. The arrow shows that velocity is a vector quantity, displacement is a vector quantity also. Okay? That's our next topic, scalar and vector quantity. We will do more on that later. Unit. Displacement has the same unit as distance, which is meter. Then time also is seconds. So that can be written as meter per second. Base unit, the same thing. Meter per second. So dimension now. That's dimension of meter. That's L. Time, capital letter T, the power of minus 1. Let's look at another one. Acceleration. Acceleration A is change in velocity over time. Change in velocity over time. So we have A equals V over T. Unit. Velocity, that's last thing we just did, meter per second. Over unit of time is seconds. So that gives us meter per second square. Meter per second square. Okay? Base unit still remain the same, meter per second square. Then dimension, that's L raised per minus 2. Let's look at force now. Force. Force is mass times acceleration. Mass times acceleration. Mass M times acceleration. Acceleration A. So formula for force is MA. Force is one of the quantities that have its own specific unit. So unit of force is Newton. Newton. In fact, and some of these units, they have their own definition too. Like force, like Newton now, you can be asked to define Newton. A Newton is the amount of force that will produce a unit acceleration in a unit mass of a body. Okay, so unit of force is Newton. So base unit now, here the base unit will change because Newton is not part of the fundamental unit, right? But we can break it down. Since force as a derived quantity, right, is obtained from fundamental quantity, then the unit should also be obtained from where? Fundamental unit. So we have to break it down so that you conform to this. And how do we do that? Just go back to the formula. What's unit of mass? Kilogram. What's unit of acceleration? That's the last thing we did. Meter per second square. So the base unit of force is kilogram meter per second square. Now it has conformed to the fundamental unit, right? So that is the essence of the base unit. If all we know about force is that unit is Newton, we won't be able to get the base unit, I mean the dimension. And once the base unit is wrong, definitely the dimension will be wrong. Because it is the dimension, it is the base unit we turn to dimension. Okay? So for the dimension now, dimension, kilogram, that's capital letter M, meter, capital letter L, time, 10 to the power minus 2. Let's look at one more. Surface tension. Surface tension, we use gamma to represent that, and that is force per unit length. Force per unit length. Okay? So the formula is gamma equals F over L. Unit now. What's unit of force? Newton. What about length? Meter. So that becomes Newton per meter. What about base unit? Base unit of Newton is kilogram meter per second square. Then times m raised to the power minus 1. Your Newton is this, then times 10 to the power minus 1. And that will give us what? That will give us kilogram, meter and per meter will cancel out. So we are left with kilogram per second square. So dimension now, dimension, that's capital letter M, 10 to the power minus 2. Okay? Let's look at another one. I want to take, at least let me take it to 10. Let me take it to 10. Number 9. Let's look at pressure. Pressure is force over area. Force over area. So P is F over A. Unit now. Unit of force is Newton. Area is meter square. So that can be written as Newton per meter square. Pressure is its own specific unit. In fact, there are about 3 units for pressure. This Newton per meter square can also be called Pascal. Pascal. Okay? We also have another unit called Torr. Another one is bar. Another one is millimeter mercury. But this is standard unit. The SI unit, Newton per meter square, what's called Pascal. 1 Pascal is written as 1 Newton per meter square. Okay? Then for the base unit, base unit of Newton, we've done that. That's kilogram meter per second square. That's our N. Then we have per meter square. So that will give us kilogram meter times per meter square will give us m raised to the power minus 1. Then s raised to the power minus 2. So dimension now. So convert this to dimension. Kilogram is capital letter M, meter capital letter L, power of minus 1, then 10 raised to the power minus 2. So that becomes the dimension of pressure. And the last one we'll be looking at is viscosity or coefficient of viscosity. That's number 10 now, viscosity. Viscosity, we use eta for that. And that is force over area times velocity gradient. Velocity, that is velocity over length. Velocity gradient. So we have eta equals F over A times velocity gradient. The L can go up, so we have FL AV. So that becomes the unit of viscosity. Unit of force is Newton. Length is meter. Area, meter square. Velocity is meter per second. So that will give us 1 meter cancel this. Okay? We have meter square. We have Newton over meter square per second. If second goes up, it becomes ordinary second. I mean, if per second goes up, it becomes ordinary second. If meter square goes up, it becomes per meter. So unit of viscosity is Newton seconds per meter square, or what we call points. We'll talk about that later. Then we have the base unit now. The base unit of Newton is kilogram meter per second square. Then that's for N alone. We have S, then we have m raised to power minus 2. Now m times m to the power minus 2 will give us m raised to power minus 1. Per second square times second will give us s raised to power minus 1. So the base unit is kilogram per meter per second. So dimension now. We make capital letter M raised to power minus 1, t raised to power minus 1. Okay? So these are the dimensions, how to obtain the dimension of some quantities. Okay? This is how to obtain some quantities. In our next video, we'll be looking at the application of dimension. Application of dimensional analysis. What are the uses of dimensional analysis? So, okay. If this is the first time you've visited this channel, please subscribe, share, and like, so that when next we upload any other video, you'll be directly notified. Okay. Then share it to your colleagues too. In the next video, we will derive more other quantities, because for us to use the dimension, we need to be familiar with the dimension of those quantities. So I may still derive some more later, and every week, every Sunday, please visit this channel as new videos will be uploaded. All right, thanks.